Good morning to you, or good evening, depending on where you are in this big, wonderful world. We are going to talk about something today that I find absolutely fascinating. It is a puzzle that nature has set out for us, a riddle that took us thousands of years to even notice, and then a very clever fellow to finally solve. We are going to talk about the way the world works when you look at it very, very closely, or when you move very, very fast. You see, most of us, we live our lives in the slow lane. I don't mean you are lazy. I mean that compared to the universe, we are practically standing still. And because we move so slowly, we have built up a lot of common sense about how things should behave. And common sense is a wonderful thing. It keeps you from walking into walls or dropping your toast butter side down. Well, maybe not the toast part, but common sense tells us how speed works. Imagine you are standing on a train platform. A train goes by at 60 miles an hour. Inside that train, a man is throwing a baseball towards the front of the train. He can throw pretty fast, maybe 10 miles an hour. Now, if you are standing on the platform and you have a radar gun, how fast is that ball going? It is not a trick question. You take the speed of the train, 60, and you add the speed of the throw, 10. You get 70 miles an hour. Simple arithmetic. If the man threw the ball towards the back of the train, you would subtract it. 60 minus 10 is 50. This is how the world works. It is what we call the relativity of old, the way Galileo and Newton thought about things. Velocities add up. If you run fast enough, you can catch up to anything. If a car is going 50 and you drive 60, you pass it. If a bird is flying and you have a rocket, you catch the bird. So for a long time we thought, well, if light is a wave or a particle or whatever it is, it must move like a baseball. We thought if you could build a rocket fast enough, you could chase a beam of light. And if you went really fast, maybe you could even catch it. Maybe you could ride alongside it, and it would look like it was standing still, just frozen there in the air, oscillating back and forth, but not going anywhere. When I was a boy, I used to think about this. What would a light wave look like if you ran as fast as? It does not make any sense when you really think about it. But nobody knew that yet. We just assumed the universe was a giant box, and time was a giant clock on the wall that ticked the same for everyone. And space was a stage that never changed. But then nature threw us a curveball. In the 1800s, we figured out electricity and magnetism. We found out they were linked, and out of the equations, beautiful simple equations, popped a number, a specific speed. It was the speed at which electromagnetic waves travel. We measured it, and it matched the speed of light perfectly. That was a big moment. Aha, we said. Light is an electromagnetic wave. But here is the trouble. The equation did not say light travels at this speed relative to the train. It did not say relative to the sun. It just said, this is the speed. That is it. That is very strange if you think about the baseball on the train. The speed of the baseball depends on who is looking at it. But the equations of electricity were saying the speed of light is just a number. It did not seem to care who was looking. So the physicists of the time, being very smart people, said, well, that cannot be right. Waves need something to travel through. Sound needs air. Ocean waves need water. So light must need something too. They called it the luminiferous aether, a fancy word for a ghostly wind that filled the entire universe. They thought light traveled at a set speed through this aether. If that were true, we could detect it. Since the Earth is spinning and orbiting the sun, we are whizzing through space pretty fast. We should be rushing through this aether wind. So imagine you are a swimmer in a river. If you swim downstream with the current, you go fast. If you swim upstream against the current, you go slow. If you swim across the current, you go at a different speed. Two very clever men, Michelson-Morley, built a machine to test this. They split a beam of light. They sent one part in the direction the Earth was moving upstream, so to speak, and the other part across the current. They bounced them off mirrors and brought them back together. They expected the light swimming upstream and downstream to take a different amount of time than the light swimming across. They set it up. They were very careful. They put the whole thing on a big stone block, floating in mercury, so it would not shake. They spun it around, they waited, and they found nothing. Absolutely nothing. The light did not care which way the Earth was moving. It did not care about the ether wind. The speed was exactly the same, no matter which direction they looked. It was as if you were running down the track at top speed, and you threw a ball, and the ball went the exact same speed relative to you as it would if you were standing still. This was a catastrophe. It was a disaster for physics. It didn't make sense. How can the speed of the beam be the same for the guy on the moving train and the guy on the platform? If I am on a spaceship going half the speed of light, and I shine a flashlight forward, I see the light move away from me at speed c. That is what we call the speed of light. Now you are on Earth watching me. Common sense says you should see that light moving at my speed, plus the light's speed, 1.5 times the speed of light. But experiments tell us, no, you on Earth look at my flashlight beam, and what do you see? You see it traveling at the exact same speed I see. How can that be? How can the same beam of light have the same speed for two people who are moving differently? This is where we have to be brave. We have to throw away our common sense, because our common sense is wrong. We have to accept the one fact that nature is screaming at us. The speed of light is the same for everyone. It is the law. But if speed is the same, something else has to give. Think about what speed is. It is not magic, it is a measure. It is distance divided by time. Miles per hour, meters per second. If I say the speed of light must stay the same, but I am moving relative to you, then the distance and the time must be changing. This is the big leap. This is where Albert Einstein stepped in and said, okay, if the speed of light is constant, then time is not. Time is not a clock on the wall that ticks the same for everyone. Time is personal. Time is flexible. It stretches and squishes, depending on how you move. Let me try to show you this with a little picture in your head. We call this a light clock. Imagine a train car again. But instead of a passenger throwing a baseball, we have a special clock. It is just two mirrors, one on the floor and one on the ceiling. A pulse of light bounces up from the floor, hits the ceiling, and comes back down. Tick-tock. One tick is the light going up and down. Now you are inside the train. The train is moving smoothly. You watch the clock. What do you see? You see the blip of light go straight up and straight down. A nice short vertical line. Up, down. Simple. But now, imagine I am standing outside on the ground, watching your train zoom by. The walls of the train are glass, so I can see inside. What do I see? When the light leaves the bottom mirror, the train is here. But by the time the light hits the top mirror, the train has moved forward. So the light didn't just go up, it had to travel diagonally, up to catch the mirror. Then as it bounces down, the train moves even further. So the light travels diagonally down to hit the bottom mirror. To you on the train, the light path is a straight line up and down. To me on the ground, the light path is a triangle. It is a zigzag. Now we know from high school geometry, or just from looking at it, that a diagonal line is longer than a straight vertical line. The path the light takes for me is longer than the path it takes for you. Here is the kicker. Here is where the universe plays its trick. We already agreed, because of the experiment, that the speed of light is the same for both of us. The light cannot speed up to cover that longer distance for me. It travels at the same steady pace, c. So if the light has to travel a longer distance for me, but it is going the same speed, it must take longer to do it. Do you see what that means? It means that the tick-tock of your clock, as seen by me, takes more time than the tick-tock seen by you. I watch your clock, and it looks like it is running slow. The time between ticks is stretched out. If you had a wristwatch on, and I could see it through a telescope as you flew by at a tremendous speed, I would see your second hand moving like it was stuck in molasses. Tick-tock. You inside the train, you see nothing strange. Your watch looks normal. You feel normal. But to me you are living in slow motion. We call this time dilation. It is not an illusion. It is not a mechanical failure of the clock. It is time itself yielding to the rule of light. I remember when I first really grasped this, it felt like the floor fell out from under me. We are so used to time being this steady marching drumbeat. But it's not. It's fluid. The faster you move through space, the slower you move through time. And it is not just time. Space gets in on the act too. If time is stretching out for me watching you, something has to happen to distance as well. Imagine you are traveling from Earth to a distant star.
You are going very fast. Because of time dilation, your clock is running slow relative to Earth. So you might think the trip only takes a few years, while on Earth, decades pass. But wait, from your perspective, inside the spaceship, you are not moving. Physics says you can say you are still, and the Earth is moving away from you, and the star is coming toward you. If you are at rest in your ship, your clock is ticking normally. So how do you explain getting to the star so quickly? You still have to measure the speed of the star coming at you as light speed, or less. You cannot go faster than light. So if the time of the trip is short for you, and the speed is limited, then the distance must be shorter. That is the only way the math works out. For you, the fast traveler, the distance between Earth and the star actually shrinks. Space itself contracts. It scrunches up like an accordion. We call this length contraction. If you measured your spaceship while you were moving past me, I would see your ship squashed. It would look shorter in the direction you are flying. You wouldn't notice a thing, but I would measure a shorter ship. So we have these two wild ideas. Time slows down and space shrinks. They work together perfectly. They adjust themselves in exactly the right amount to keep that one number, the speed of light, safe and constant. It is like a cosmic conspiracy. The universe will distort its very geometry to prevent you from ever seeing light move at a different speed. Now you might ask, and you should ask, okay, this is very strange, but why does it matter? It sounds like a philosophical game. It matters because it is real. We see it every day in the lab. We have particles called muons. They are created high up in the atmosphere by cosmic rays hitting the air. These little guys are unstable. They fall apart. They decay very quickly. They live for such a short time that even traveling near the speed of light, they should not be able to reach the ground. They should die long before they hit the surface of the Earth. But they don't. We detect them down here all the time. How? Because they are moving so fast. From our point of view, their internal clock is running slow. Their short life is stretched out, giving them enough time to reach us. From their point of view, the atmosphere is squashed thin, so the distance they have to travel is much shorter. Without this bending of reality, we wouldn't see them. So we have established that the world is not what it seems. We have established that to keep the speed of light, the limit, space and time have to be flexible. But this brings us to the big question, the one you are probably wondering about. Why is there a limit at all? I mean, okay, strange things happen when you go fast. Your clock slows down. But why can't I just push the gas pedal a little harder? Why can't I just add a little more fuel, burn the engines a little hotter, and break through that barrier? Newton says if I push something, it accelerates. If I keep pushing, it keeps accelerating. If I push forever, I should go infinitely fast. Why does Einstein say no? Is there a wall? Is there a policeman in space? Is the air too thick? No, it is something much more fundamental. It has to do with the stuff you are made of. It has to do with energy itself. You see, we usually think of mass, how heavy something is, or how hard it is to push, as a fixed thing. A bowling ball has a certain mass. It doesn't change whether it is sitting on the rack or rolling down the lane. But remember, we just found out that time and length are not fixed. So why should mass be safe? This leads us to the most famous equation in the world. You know the one, E equals mc squared. People print it on t-shirts, but they rarely stop to think about what it really tells us about moving fast. It tells us that energy and mass are cousins. In fact, they are the same thing, just dressed up differently. When you heat up a cup of coffee, you are adding energy to it. Heat energy. According to Einstein, that cup of coffee actually gains a tiny, tiny bit of mass. It gets heavier in a sense, because you added energy. Now think about motion. Motion is energy, kinetic energy. When you push that rocket ship, you are pouring energy into it to make it go. At slow speeds, like in a car or a jet, this energy just makes you go faster. The mass effect is so tiny you can't find it. But as you get closer to that magic speed limit, the speed of light, something funny happens. The energy you put in does not just go into speed anymore. It starts to go into heaviness. I want to be careful with words here. Modern physicists don't like to say the mass changes. They prefer to say the momentum changes. in a weird way. But for us, thinking about it intuitively, it is as if the object is getting heavier and heavier the faster it goes. Imagine you are pushing a shopping cart. Easy. Now imagine that every step you take, the cart gets filled with lead bricks. It gets harder to push. You have to push harder just to get a little bit more speed. As you approach the speed of light, your rocket ship behaves like that shopping cart. You dump in fuel, you fire the engine, you generate a massive amount of energy. But instead of zooming past the speed of light, the universe takes that energy and converts it into inertia. The ship resists you. It fights back. To get to 90% of the speed of light takes a lot of energy. To get from 99% to 99.9% takes a staggeringly huge amount. And here is the mathematical wall. If you try to calculate how much energy you would need to reach 100% of the speed of light to actually hit C, the equation blows up. It goes to infinity. You would need infinite energy to push a single electron to the speed of light, and there is not an infinite amount of energy in the universe. So you can't do it. It is not a technical problem. It is not that our engines aren't good enough. It is the law of the bank. You cannot pay an infinite cost. So material things, you, me, rockets, dust, we are forever trapped below the speed of light. We can get close. Oh, we can get very, very close, but we can never touch the limit. But then, what about light? If we can't do it, how does light do it? Light travels at the speed of light. It's in the name. This is where the distinction between matter and light becomes beautiful. The reason you and I have this problem is that we have mass. When we are standing still, we have rest. That is the seed that grows into the infinite problem when we move. But a particle of light, a photon, has no rest mass. It weighs nothing. Zero. Zip. Because it has no mass to start with, it doesn't have the heavy problem. It doesn't need a push to get going. In fact, it cannot sit still. A photon is born moving. The moment it is created by a candle, by the sun, by a light bulb, it is already going at C. It has no choice. It exists only at that speed. If you could slow a photon down, it would vanish. It is a creature of pure speed. So C is not just a speed limit for rockets. It is the natural speed of anything that has no weight. It is the speed of gravity waves. It is the speed of the glue that holds atoms together. It seems like C is the speed at which the universe talks to itself. It is the speed of information. If the sun disappeared right now, popped out of existence, we wouldn't know it for 8 minutes. We would still see it shining. We would still feel its gravity pulling us in orbit. The news of the sun's disappearance travels at the speed of light. Gravity travels at the speed of light. Nothing can outrun the news. And this leads to perhaps the strangest part of all, the part that really messes with your head. If you could go faster than light, if you could beat the news to its destination, you would start to break the logic of the universe. We talked about time slowing down. Well, the math says that if you hit the speed of light, time stops. Frozen. If you were a photon, you wouldn't experience time. You would leave a star 1 billion light years away and arrive at Earth instantly. For us, 1 billion years passed. For the light, 0 time passed. Now what happens if you go faster than that? If you follow the graphs, if you follow the lines on the paper, going faster than light implies moving backwards in time. This is why the speed limit is so strict. It is not just about energy. It is about protecting the story. Cause and effect. The cause must happen before the effect. You pull the trigger, then the gun fires. You drop the glass, then it breaks. If you could travel faster than light, there are ways to arrange things, depending on who is watching, where the glass breaks before you drop it, where the message arrives before you send it. You could send a message to your past self, saying don't send this message. Then what happened? The universe gets tied in a knot. So the speed of light is like the cosmic sensor. It prevents us from seeing the future before it happens. It keeps the timeline in order. It ensures that now leads to later, and not the other way around. It is a fascinating thought, isn't it? That this specific number, 186,000 miles per second, is the only thing standing between us and total chaos. It is the wall that defines reality. In the next part we are going to look a little deeper into this. We are going to ask, Is it really impossible? Are there loopholes, wormhole, warp drives? We all watch science fiction. We all want to go to the stars. But for now, just look at a light bulb, turn it on, snap your fingers. That light hits the wall instantly, but it's not instant. It's just very, very fast. And in that tiny delay, in that finite speed, lies the secret to the structure of space and time itself. It is wonderful that the world is built this way. If it were built the common sense way, it would be boring. But nature is not boring. She is full of surprises, and the speed of light is one of the best surprises she has. So stick with me. We have only just scratched the surface of the impossible. Welcome back, or if you are just joining us, pull up a chair. We have been talking about the strange rules of the road in our universe. We talked about how clocks slow down when they move fast, and how space itself gets squeezed. It sounds like a fairy tale, doesn't it? But it is as real as the chair you are sitting on. We left off with a bit of a cliffhanger. We found out that you cannot push a rocket ship to the speed of light because it gets too heavy. We said that energy and mass are two sides of the same coin. But I want to dig a little deeper into that, because it is one of those things that is easy to say, but hard to really feel in your gut. Think about money. I know physics is usually about atoms, but let's talk about money for a second. Imagine you have a bank account. In this bank, you can deposit mass, or you can deposit energy. The bank teller doesn't care. To the teller, it is all just currency. When you are standing still, you have a certain amount of currency in your account. That is your rest mass. It is the cost of just existing. For a human being, that is a huge amount of energy, by the way. If we could turn you entirely into pure energy, you would explode with the force. Thousands of hydrogen bombs. Please don't do that. We like you the way you are. Now you want to move. To move, you have to pay the bank. You have to deposit kinetic energy at slow speeds, like walking or driving. The fee is small. You put in a little energy, you get a little speed. The bank balance goes up slightly, but you hardly notice. But here is the trick. This bank has a weird exchange rate. The faster you go, the more expensive the next mile per hour becomes. There is a number in the equations. We call it gamma. You don't need to memorize the Greek letter, but you should know what it does. It is a magnifying glass. When you are standing still, gamma is equal to 1. Nothing changes. When you go 50% of the speed of light, gamma grows a little bit, but as you get to 90%, 99%, 99.9% of the speed of light, this gamma number starts to shoot up to the sky. It goes to 10, then 100, then 1,000,000. This gamma factor multiplies your mass. So effectively, your rocket ship, which weighed 100 tons on the launch pad, now acts like it weighs 100 million tons. Imagine trying to push a mountain with a bicycle motor. That is what it feels like to try to accelerate near the speed of light. You are pouring fuel into the engines, burning everything you have, but you are getting almost no extra speed out of it. Where is the energy going? It is being stored as mass. You are getting heavier, not faster. And if you try to reach the limit, 100%, the gamma number becomes infinite. The bank demands an infinite deposit. The universe says sorry, insufficient funds. This is why we say, the speed of light is a horizon. You can see it, you can move towards it, but no matter how long you chase it, you can never quite stand on top of it. It always stays just a little bit ahead of you. Now you might be thinking, okay, I get it. I am too heavy, but what if I wasn't? What if I could cheat? Well, let's look at the things that do travel at that speed. We call it the speed of light, which is a bit of a selfish name for us to give it. We noticed light first, so we named it after light, but it is really the speed of massless things. Gravity, for instance. We used to think gravity was Newton thought that if the sun vanished, the earth would fly off into deep space. At that exact same moment, he thought gravity was a magical rope that connected things instantly across the universe. But Einstein showed us that gravity is not a rope, it is a shape, it is a curve in space. Imagine a trampoline. You put a heavy bowling ball in the middle, the fabric curves down. That is gravity. Now roll a marble nearby. It follows the curve. What happens if I suddenly yank the bowling ball away? Does the fabric instantly snap back to flat everywhere? No, a ripple moves out. The fabric snaps back in the middle, then a little further out, then a little further. That ripple travels across the trampoline. Space is the same. If the sun disappears, a ripple in the fabric of space travels outward. That ripple is a gravitational wave, and guess how fast it moves? Exactly the speed of light. So C is not just about brightness. It is the speed of gravity. It is the speed of the strong force that holds the nucleus of an atom together. It is the speed limit of reality's operating system. It is the maximum speed at which one thing in the universe can affect another thing. It is the speed of cause and effect. And this brings us to the most mind-bending part of the story, the real reason why you can't break the limit. It is not just because you are heavy. It is because if you did, you would break logic. You would murder history. We need to talk about simultaneity. That is a big word, but it just means happening at the same time in our everyday life. At the same time is if I clap my hands and you clap your hands, and we see it happen together, we say it was simultaneous. We think the whole universe agrees with us. We think there is a giant now that stretches across all the galaxies. But remember the train from before, the one with the light clock. Let's do another experiment on that train. This is a famous one. Imagine you are standing in the exact middle of a long train car. You have a lamp. You turn it on, light beams go out forward and back. Since you are in the middle, the light hits the front wall and the back wall at the exact same time. Easy. But I am watching from the platform. The train is moving forward very fast. I see the light bulb turn on. The light moves forward towards the front wall and backward towards the back wall. But the train is moving. The back wall is rushing towards the light beam. The front wall is running away from the light beam. So from my point of view on the ground, the light hits the back wall first. It has a shorter trip because the wall came to meet it. The light hitting the front wall happens later because it has to catch up to the fleeing wall. And do you see the problem? For you on the train, the two hits happened at the same time, simultaneous. For me on the ground, they happened at different times, not simultaneous. Who is right? We both are. Simultaneity is relative. What is now for you is not necessarily now for me. We slice up the loaf of space-time at different angles. Now usually this is just a curiosity. Oh, the clocks don't agree. How quaint. But if you could go faster than light, this disagreement turns into a nightmare. If you go faster than light, you can escape your own light cone. Imagine a pond. You throw a rock in, ripples spread out in a circle. Those ripples are the speed of light. If you are a bug in the water, and you can swim slower than the ripples, you are always inside the circle. Everything you do, every influence you have, is inside that expanding circle. But if you are a superbug, and you can swim faster than the ripples, you can get out ahead of them. You can be in a place where the water is still calm, where the news of the rock hasn't arrived yet. In the geometry of space-time, if you go faster than light, you are technically moving backwards in time, relative to some observer. Let's say you have a gun that shoots super fast bullets. Faster than light, you are standing a mile away from a target. You pull the trigger. For you, the bullet leaves the gun and hits the target instantly. But for someone flying past in a spaceship at a certain speed, the order of events flips. They would see the bullet hit the target before you pulled the trigger. They would see the hole appear in the target, then the bullet fly backwards into your gun, and then your fingers squeeze the trigger. This is not a magic trick. This is just how the math of space and time works. If you break the speed limit. Now imagine you are the target. You have a super fast telescope. You see the bullet hit you. Then you send a super fast message back to the shooter, saying don't shoot. Because your message is also faster than light, it can travel back in time, relative to the shooter. The shooter gets the message don't shoot before he pulls the trigger, so he doesn't shoot. But if he doesn't shoot, the bullet never hits you, so you never send the message, so he does shoot. We have a paradox, a logical loop, that cannot be solved. The universe does not like these. They are messy,
They break the chain of cause and effect. Physics is at its heart the study of how one thing leads to another. If the effect can prevent the cause, the whole structure collapses. The story makes no sense. So many physicists believe that the speed of light is strictly enforced, not just to annoy rocket builders, but to preserve the sanity of the cosmos. It keeps yesterday in the past, and tomorrow in the future. It creates an orderly flow of events, so that the universe can evolve. It protects us from chaos, but surely, you ask, there must be a way around it.
What about wormholes? What about warp drive? I saw it on TV. Well, nature has a wonderful imagination. Often her imagination is better than ours. The equations of general relativity, Einstein's masterpiece, actually do allow for some loopholes. But they are very, very expensive loopholes. Take the warp drive. The idea is that instead of moving through space, you move the space itself. You shrink the space in front of you and expand the space behind you. You ride a wave of space like a surfer. Inside your bubble, you are standing still. You aren't moving faster than light locally. The light beam next to you is still faster than you, but the whole bubble is moving faster than light relative to the outside world. It sounds perfect. No time dilation, no getting heavy. The problem, to make space expand and contract like that, you need energy. But not just normal energy, you need something with negative mass. You need negative energy density. We have never found a chunk of negative mass. We don't even know if it can exist in large quantities. Gravity pulls, negative mass would push. It is exotic stuff. If it exists, it is rare and hard to catch. And then there are wormholes. The idea that you can fold space like a piece of paper. Instead of traveling all the way across the sheet, you punch a hole through the folded layers. You step through a door here and come out near Andromeda. Mathematically, it is possible. Physically, it is a nightmare. A wormhole is inherently unstable. The moment you try to step through it, gravity wants to snap it shut. It would crush you instantly. To keep it open, again you need that exotic negative energy to hold the throat of the wormhole open, to push against the crushing gravity. And even if you could build one, the paradoxes come back. If you move one end of the wormhole around at high speeds, you can turn it into a time machine. You could step through and come out yesterday. And then we are back to shooting our own grandfathers and breaking the universe. So while we can write the equations for these things, nature seems to put up do not enter signs everywhere we look. Every time we find a loophole, we find a physical law that seems to plug it up. Stephen Hawking called this the chronology protection conjecture. The idea that the universe creates laws specifically to prevent time travel and keep history safe for historians. It is frustrating in a way. We look up at the stars and they are so far away. Even at the speed of light, it takes 4 years to get to the nearest one. It takes 100,000 years to cross our own galaxy. And there are billions of galaxies. We are stuck on a little island in a vast ocean, and the speed limit means we might never see the other shore. But I don't look at it that way. I think there is a beauty in the limit. Think about a game like chess. If you could move any piece anywhere instantly, the game would be meaningless. The beauty of chess comes from the rules. The knight moves this way. The bishop moves that way. The constraints force you to be creative. They create the structure of the game. The speed of light is one of the foundational rules of our game. It forces the universe to have structure. It creates local neighborhoods. It allows stars to burn for billions of years without exhausting their energy instantly. It allows us to look back in time when we look at the sky, seeing the history of the universe written in ancient light. If light were instant, the night sky would be a blinding white wall, because the light from every star in infinity would reach us at once. The darkness of the night sky, Olber's paradox, is actually evidence that the universe has a speed limit and an age. So the next time you look at a star, remember that you are not seeing it as it is, you are seeing a ghost. You are seeing a message from the past, carried by a photon that has been traveling for 1,000 years, dodging gas clouds, flying through the emptiness, never slowing down, never resting, holding on to its precious cargo of information, just to hit your eye and tell you I was here. The speed of light is the ultimate limit, yes, but it is also the ultimate connection. It weaves space and time together into a single fabric, space-time, where energy, mass, and motion dance together in a complicated, beautiful ballet. We may never break the speed of light, but in trying to understand it, we have broken the limits of our own imagination. We have learned that the universe is far stranger and far more wonderful than our ancestors ever dreamed.
And that to me is the best kind of adventure. Thank you for listening.